We have a table of data here, and we'd like to see if it's linear, and if it is, find the slope and y-intercept. Now, the inputs are not equally spaced, so we can't just check the first differences. So we're going to have to look at the slope in each case, so each pair. So 0.5 minus 5.5 over 3 minus 2. That's doing this first pair here. We get negative 5 over 2, or negative 2.5 as a decimal. We go to the next one. Negative 7 minus 0.5 over 6 minus 3. So now we're looking at these two. That's negative 7.5 over 3. Which, again, so let's put these all in decimals. This is negative 2.5, negative 2.5. So we keep getting the same thing. We'll do a couple more. I think you're going to see a pattern here. Let's do this pair right here. So we're going to do 12 minus a negative 7. So we're doing 12 minus, oh, excuse me, that should have been a negative 12 over 8 minus 6. And this is going to be 12 basically plus 7, negative 12 plus 7, which is negative 5 over 2 equals negative 2.5. For time's sake, I'm not going to check all of them, but that's one of the ways we could do it. You could put it into a graphic calculator, do linear regression, and also check it that way. We have a constant rate of change, and in fact, we have found our slope. Now, there's a couple different ways we can actually find the y-intercept. One is we could build the model, and we could find it that way. But let's use what we know about linear functions to work off of this. Well, we know that when x equals 1, y equals 5.5, and that every time x goes up 1, it goes down 2.5. Well, we want the y-intercept, which means we want when x equals 0. So instead of going instead of going down 2.5, we're actually going to go up 2.5 to get our corresponding y value. So that x gives that y value, this x goes y, which is 8. And notice that's corresponding to where the input is 0. So this would be our b. Again, you could have made the linear equation and found it that way. This is just another option.